time response analysis or analysis in time domain. What do you mean by this time domain analysis or time domain methods? Does something comes to your mind? What is this I am talking about? Like just recently we saw root locus Routh-Hurwitz criteria for determining stability, right? We call these methods as time domain methods. We call them as what? Time domain methods when we are talking of either your root locus or for that matter Routh criteria, right? Routh stability technique. These are your time domain methods. These are said to be what? Time domain methods. Now, what is time domain methods? Why do we call them as time domain? And now today I would be starting with frequency domain methods, or looking output in frequency domain, which will be called as frequency response. When we see output in time domain, here you can see in this figure, we have both frequency domain and no time domain output, right? Graphs. So can you tell something quickly, someone, what you understand that from this term that root locus and Routh method, they are time domain tools for stability analysis. When we talk of time domain, yes, Ben, I should give you chance. Would you try to answer? Anyone for that matter? Yes, Shri has joined today. Yes, Ben, would you answer?
Not exactly sure, sir.
You answer what you understand. Time domain means what? See, we had this standard second order response, right? To a unit
Hmm.
step input, second order underdamped response, right? Yes or no? So, what is
Yes,
on y axis, Ben?
amplitude output.
No, y axis is C of t.
Yeah,
Y axis is what? Output C of t, and x axis is what? Time
time.
t. So here we call this as time response. What do this C of t here I am calling this in this sketch? I am calling this as what? Simple English meaning time response. What I am calling this as?
Time bus.
Time response, because here I can see response. Response is nothing but output as it varies with respect to time t. Right? When I see the variation of output with respect to time t, I call that as what?
Time bus.
Time response, right? When it is varying against time t, it is time response. Capital T, capital R stands for time response. When I am able to see the same output, right? Now, as a variation in frequency omega, I will call that as what? Frequency response. So here it is little weird. I should not write C of t, right? I should write what? Let us say C, or no C of omega, small c. So when the output I see, how it presents itself on varying the frequency of the input signal, I see that quantity as what? Frequency response. Response stands for output. When output is obtained against time t, time response, when the output is obtained against frequency omega, we call this as what? Frequency response. It's very simple. Yes or no, friends? Now, when we talk of root locus and Routh-Hurwitz, what information do we get from that? Yes, the information we get is about the possible pole locations, right, in S plane. Yes or no? What do we get? We get some possible pole locations in S plane by evaluating these two techniques, Routh criteria What does Raoult's criteria tells us? Yes,
About
friends.
stability.
Stability, good. But what more does it tells about? It tells about whether or not there are any poles in the right half of the S plane or not. You are correct. It tells about stability, but probing more, it tells about what? Whether there are any poles in the right half of the S plane or not. Yes or no?
Yes.
If the first column of Raoult's array has no sign changes, we say there are no poles, right? When there are no sign changes in the first half, in the first column, when there are no sign changes in the first column, we say there are no poles. Where? In the right half of S plane, right? When there are no sign changes in first column, we say there are no poles in the right half of the S plane. Now, similarly from root locus also what we get to know, yes, some branch is going here, originating here, some branches are going like this, right? So some peculiar root locus, right? So what do we get from root locus? From root locus also we get to know about likely pole positions, likely pole locations, right? That is what we get to know from root locus. And pole positions, they tell us about what? Yes, Ben. If I have a no pole like this, a second order system, if I have pole like this, what will be the response here to a unit
Or
step input?
sustained oscillations.
Sustained oscillation, right? In case I have poles like here, then what will be the output? Output will be what? Damped
Damped.
oscillations, right? So these pole positions are letting me know the response. Now, what is this on t-axis in each of these sketches? What is on t-axis? Time t. What is on t-axis? Time t. And what is on y-axis? Output c of t, right? So these pole positions are only letting us know what? The nature of response, right? With respect to time t. Yes or no, friends? The step response, whenever we say step response, it let us know the nature of response, right? With time t, right? Step response is that is response obtained when system is subjected to a step input. Or in case if you have no roots like this, they are not imaginary or complex, but they are real, then what will be the response? It is as shown here. The response will be what? Exponential, without any uh, oscillations witnessed in the initial part of the response. So each of this is called a step response. What is each of this called as here, friends, students? Yes, this response or this response or this response. Each of that is called as what? A step response. And step response is something very normally associated with what? Time response, right? Normally, whenever we want to see the time response of a system, we try to obtain its step response, as in most of the cases we have seen, right? And in route Harvit's array or root locus technique, we get to know the response of the system against time t by completing or by evaluating the tools routes stability criteria or the root locus technique. So both the root locus and route Harvit's criteria help us to know the time response of the system. Remember, these are not helpful or used in knowing the frequency response. Did I made clear first of all what is time response and why do we call root locus and routes stability criteria as tools used in time response analysis or time domain tools?
Yes, sir.
Good, right? So once that is clear, why do we call them, right, as tools available for analyzing the system, its output, its stability, with respect to time t. Now, next, let us understand frequency response or frequency domain tools. We will study two very important tools in analyzing stability of a system in frequency domain. One will be called as Bode plot, very popular, huge application, right? Everywhere. And little EC students may have advantage since they have studied signals and systems, and also I think DSP, so they may have more insight about what I mean by frequency spectrum, or frequency behavior, or projection in frequency domain. So I want my pencil here. Yes, 1 minute. Yeah. So I was talking. We will have two very important tools in frequency domain to be used for understanding the output of the system. One is called as Bode plot, right? I hope I am able to generate interest among you guys that you take it forward. It is used very much even in research and further studies. So one is Bode plot and second is Nyquist plot. Nyquist plot or Nyquist contour. Okay, Nyquist plot. So these two would be there studied for again stability analysis. These two will be telling for what? Telling for stability determination of system, right? But in what? In frequency domain. But in what? Frequency domain. Frequency domain means what? When you are in plane frequency, when you are witnessing what? Against scale frequency. Time domain means what? When you are witnessing output against time axis, right? So in frequency domain, this two will be what your tools that will be used to analyze the stability of no system. Same system can be uh, analyzed, can be seen either in time domain or in what frequency domain or in both the domains, right? And as I said, frequency domain means when we are in no frequency plane, right? When we are looking at the behavior of the system and its output with respect to change in frequency of the input signal. To refine it further, let us understand the define terminology for frequency response. Now it tells us the steady state response of the system to a purely sinusoidal input, right? The steady state response of a system to a purely sinusoidal input is defined as what? Frequency response. And as this frequency of the input is changed from omega equal to 0 to omega equal to infinity, how the changes occur in the steady state of the system response, right? Will help us to plot no, these two quantities and determine the frequency response for the system in hand. So steady state, because we saw your no time domain no graph. We saw the output for a underdamped system has initially oscillations and later on what? It steadies. Even if it is overdamped, it exponentially rises, right? And not exponentially, it rises initially and then steadies itself. So we will pick up that steady part of the output, right? When it has stopped varying with respect to time t, that studied output of the system, how that studied output changes to changes made in the frequency of the input signal, will give us a sketch between output and frequency omega of the input, and which we will call as frequency response. So here for you, there are two responses, right? In the left hand figure, is the figure visible enough, everyone? Yes. In the left hand figure here, you have the time response, right? And in the right hand figure, you have frequency response. So this is how the output will look, right? Or system behavior will look like when we are in frequency domain. And this is normally which we have been encountering, looks like when we are in what? Time domain. This is simple step response of a second order system. It may be a overdamped system where there is no oscillations generated in the initial part, and response rises initially and steadies down after some time. And you can see after this 0.98, I think, no, 0.98 is different. After this 4t, or I think it is first order system, right? For first order system, settling time is 4t, rise time is 2t, right? Where capital T is the time constant. Yeah. So once the response has steadied itself, right, then that is what we see. So how this part will change when we change the frequency omega of the input signal. So here you see on the right hand side, now I have one sketch, the y-axis of which is called as what? M. Now here I see M is nothing but the magnitude of what? The system, right? The magnitude of the some characteristic function, right? It is nothing but your transfer function only, changed or modified slightly. So that is on y-axis, modified magnitude of the no characteristic function of the system, and x-axis is omega. So when we plot this magnitude against omega, what we get is frequency response, right, friends? Now here you see what do we mean by this. Now if I have a linear system, right, which we are restricted ourselves in in our discussion of control system. So in analyze in determining frequency response, one important thing that is to be remembered is the input that will be given to system will always be a sinusoidal input. Yes, like mostly in time response, what input do we use to analyze the system output? For time response, we use which input? Most of the cases, we use a step input, right? Or you can use ramp input or parabolic input, but right, one of them mostly used is what? A step input, since we know the transients or the transient part of the response is independent of input and it depends on system poles. So once studied for a step input, it need not be again further no used for or subjected to ramp and parabolic input. Our conclusion will remain same. Now when we are with frequency response, the input that we are going to use is a pure sinusoidal function, sine of omega t, right? So here you can see the input given to a system, right? Let us say you have a system, right? This is system. The input that is coming to it is a sinusoidal input, and the output that you are obtaining from the system c of t. For a linear system, we know when there is a sinusoidal input, output will also be what? A sinusoidal output. But what may vary? These two terms may vary, right? Of the output when system is subjected to a sinusoidal input. These two terms that I have encircled. One is called the magnitude of the output or the amplitude of the output, and another is called as phase term. This is called as magnitude, right, of the output, and this is called as the phase term, right, of the output. Now what we do, we will accumulate the different values of b and phi as I change omega, right? So when I plot this b versus omega, the resultant plot will be called as magnitude plot in frequency response. And when I change phi, when I plot phi versus omega, the resultant plot will be called as phase angle plot or simply phase plot in frequency domain. So in frequency domain normally you may see magnitude and phase. In Bode plot, it will be two plots, whereas in Nyquist plot, it obtains the complex function itself with respect to omega. Quite interesting that we will see. So this is what we will see. when we are talking of frequency response, how the magnitude of the output, right, and the phase of the output changes to changes in the uh, frequency of the input signal. That is called as frequency response. Guys, can any one of you summarize what I just said for last 10-15 minutes? Yes, yes, someone. Yes, Shrivali Sarvani, would you like to tell us what is frequency response? Shrivali? Yes, Shrivali is busy in breakfast, munching some dosa. Okay, Ben, would you tell something about frequency response?
Yes, sir. So frequency response, we do the system analysis in frequency domain with respect to omega axis. So here we do the analysis for a sinusoidal input.
Yeah, very important. In frequency response, the input is fixed. What is the input? A pure sine function, right?
Yes,
A pure sine function will be the input that will be always used to investigate the output of a system in frequency domain, which will be called as frequency response. And what is that we obtain in frequency domain? The variation in the magnitude of the output against frequency omega, right? I don't see a variation in B or phi by varying capital A. What is capital A? The amplitude of input
mm,
sinusoidal signal. I am not worried about what is capital A, right? Because change in A will not bring no to me any change in this B and phi. They will remain no independent of that. But B and phi will see a significant variation to changes in the frequency of the input signal. And this characteristic of change in magnitude and phase of the output with respect to change in the frequency of the input signal is called as frequency response. And that is what we see here, right? In the figure on the right hand side, you have a frequency response, right? How the magnitude is changing. Magnitude is close to 1 at frequency omega equal to 0. Can you see, Ben, this screen?
yes, sir.
So frequent magnitude is something called as MR, which we will call as resonant peak at some value of omega r resonant frequency. And you see the magnitude decreases and approaches 0 as omega increases and approaches infinity. Initially magnitude was 1, later it hit some peak with increase in omega. Further increase in omega witnesses decrease in magnitude, which steadily is now no, on decline and approaches 0 for higher values of omega. This sketch is called as frequency response, right? Or the no frequency domain no representation for the system output. The variation in its magnitude, here it's only magnitude plot is shown. Similarly, there will be a phase plot, I will tell you. So I think it's quite clear, guys, what is time response and frequency response. Time response, you see the no t variation of the quantity with time t. In frequency response, you see the variation with respect to frequency omega, where omega is the frequency of the input no given to the system. So let us quickly move further, right? So that's what I have collected here, information for you. It's quite easy and interesting, friends. Keep yourself involved. It will be quite easy then. Yeah. Now we have some comparison between frequency response and time response. Now, one of the most important, I have gathered so many points, you can read it always. But to my, no, this uh, knowledge, the appreciation is in frequency domain, the appreciation is most important advantage is ease of modeling. Ease of what? Modeling. Sorry, yeah, ease of modeling in that is in frequency domain compared to what in time domain, right? What does this mean that there is ease of modeling in frequency domain? This mean if I have a system, right, if I have made a system and I want to obtain its transfer function, right? Normally, how is the transfer function? We see transfer function something like s10 divided by what? S square plus, or let me write it in standard form, or I don't know which form here, let it be omega n square upon s square plus 2 zeta omega ns plus omega n square, right? So this is one in zeta and omega n, or another we have in some a and b form also. We have s plus a, right, into s plus b, right? Or we have something k upon what? S s square plus bs plus a, right? Or let me call it a. So either in any form, when I have these values, right, zeta omega n here, or a and b here, or a and b here, I say I have obtained the transfer function of the system. What do I say? I have obtained the transfer function of the system, or I have modeled the system, right? I have modeled the system. So the ease of modeling is much more in frequency domain, right? Because you will very soon see that there are some frequencies, right, which will be related to the existence of poles in the complex plane called as corner frequencies. We will see soon. Those are very relatively obtained quite easily. Otherwise, if we want to model with help of a no time domain technique. In time domain technique means I have to just we saw above. I have to obtain the step response, right? If I have, let us say, applied a unit step input, and this is my output to the step input. Then from this step response, it's not that easy. It's more complex and tedious to obtain the model of the system. Are you getting me, Ben? I am talking here on behalf of students. You answer me. If this is a system and I want to obtain its transfer function, right? If I am applying here a unit step input and the corresponding output CT, right? It will be something like this here, shown here. Whereas if I apply a no a sinusoidal signal, right? A sinusoidal signal like a sine of omega t, and I vary omega over its full range from 0 to what infinity, and for each omega I am collecting the corresponding output. I have already broken down in terms of two quantities, magnitude and phase angle phi. So when I say I am collecting output, I am collecting magnitude and phase angle phi for each of the frequency omega. And here I will get something like this, right? Huh? So from here I will know, I can find out very easily where are some no likely corner frequencies that exist. So there will be some quantities called as corner frequencies that will be very easily identifiable in case of frequency response, and I can directly relate the existence of those corner frequencies fc1 and fc2 to the pole position, and I can represent obtain this a and b coefficient, because we know when we solve this we get pole positions only, right? So if I am able to establish pole positions, I can know go back and get the corresponding no factors that will be forming the transfer function. So one most important thing in frequency domain analysis is the ease of modeling of the system. That comes to me as no one of the no highlight of frequency domain methods. Second one to talk about will be relative stability. Did you understand first one? Anyone has a question here? So not reliability, relative stability. Let me write here number two, relative stability. Can anyone tell me what you understand by relative stability? Guys, keep yourself motivated. I need you guys to involve, take interest, learn thing. This is a very fundamental design level course that forms no foundation for any modeling and no further research if you pursue and a scope so wide a scope. So what is relative stability? I expect some of you to tell me. I have been talking this for a while now. This is
And
second
we want to
advantage.
compare different systems stability.
Yeah, it tells me no about two systems, right? Which one in a given circumstances offers me higher no stable outputs, stable no behavior. So that relative stability information is not at all coming out from what you are easily, right, coming out, but not easily either from route method or root locus or simply in no time domain analysis, right? Because here you see I have drawn one underdamped response, right? It will have its own percentage overshoot, settling time, everything. I will draw one more no system which is also underdamped. So it's not very easily. You have to have no complex analysis and analytically obtained to some result to tell which one is no giving you more no stable, or you have to find out all those terms like settling time, percentage overshoot, right, Ben? So then you would be able to tell which one is no better. Immediately on inspection you can't tell this, but this in frequency domain is not the case. In frequency domain, the inspection and no of the system, right, response allows you to relatively identify the better among the no given responses. So this is another very important aspect of comparison between time response and frequency response, right? Or in time domain analysis and frequency domain analysis, it is of relative stability. First one was ease of modeling, second one is of relative stability, right? So there are many more. You guys can always read it, right? And I may ask you something there in quiz or assessment exam, then you guys can accordingly answer it, right? But this too remains no at the core, right? All that only is written here. Accurately measuring time response to a step input is difficult, right? Then all blah blah you have to read it. So there are this no uh, advantages of one above another. Oh, so many I have collected. Yeah, this is also important. The effect of noise signal are assessed easily in frequency domain. Right, always when we have a system, some noise no penetrates, enters into the system. So how well we are able to assess its introduction and how well we are able to filter all that, we are much no comfortable with when we are in frequency domain rather than in what time domain. So noise effect also has one no distinct point of comparison between frequency response and time response. Controller design also, the first point is telling is more no comfortable when we are tuning or designing a controller. The frequency response is no preferred over time response techniques. The last one here is telling this frequency response can be applied for non-linear systems, something interesting. Yes, the time domain which we have seen are mostly restricted to linear systems. Okay, that is also one good thing. Then Yeah, it is telling determining response of higher order system. Yeah, this is also quite easy. When if you are having a transfer function of third order or no higher, will it be easy for you without calculator in hand to obtain the time response? To
No, sir.
obtain time response, you need to factorize, right? You need to find out the three poles. Third order transfer function means three poles. So
Mm.
you have to factorize it. And if it is further up in order, then it's more complex, right? But third order itself, we don't have no that much convenience to find out two factors and then to write down the poles. So, but here you will see whether it is third order, fifth order. With ease, I would be finding out the response. Response means the magnitude plot and the phase plot against frequency omega in frequency domain techniques like Bode plot and your Nyquist plot. So that is also one point to be kept in mind. So that's so many of no comparisons. You guys are free to read it, but please do read it. So it still continues having magnitude and phase. Yeah, okay, it's same thing. Yeah, another one important thing, friends, I wanted and I missed it while introducing frequency response is how do we start no obtaining frequency response. So you have to be very no clear about it. Now, whenever we are given a transfer function, normally transfer function is given as what? T of s equal to, let us say, 4 upon no s square plus 3s plus 4. Let us say we are having a transfer function. Now, when it comes to frequency response, I say that the input applied is always a sinusoidal signal, right? And in frequency response, I obtain the magnitude and phase of the output for different values of input frequency omega. So what we do, this transfer function, we first convert into a sinusoidal transfer function. What we do, we convert this into a sinusoidal transfer function. How do we do this? Simply by replacing s by j omega in the given transfer function. So when I do this, t of s becomes t of j omega, and that will be equal to 4 upon minus omega square. When I put s equal to j omega, it will be minus omega square plus j 3 omega, like plus 4, right? So here I have got transfer function, sinusoidal transfer function. And what do you tell about this? Yes, Ben? Yes, it's nothing but a complex quantity. Yes or no? So I can write down this as what? Simply 4 upon 4 minus omega square, that is the real part in denominator, plus j3 omega. So when I want to write magnitude of this, what will be magnitude of this? It will be 4 into what? Yes, divided by under root of 4 minus omega square whole square plus 3 omega whole square, right? And angle phi will be what? Angle phi will be minus tan inverse of what? 3 omega by 4 minus omega square. Are you getting this, friends, what I am doing? This is a complex quantity. Once we have got a sinusoidal transfer function obtained by replacing s with j omega, then simply I go on to obtain no magnitude. We know a plus jb as a magnitude of, yes, a plus jb has magnitude of what? Under root a square plus b square. And what is the phase angle? Phase angle is given by tan inverse of imaginary by real, right? Since it is in numerator, right? Simple. So it is tan inverse of this. Here the complex quantity is in denominator. So in phase angle contribution, it will be minus. So I have obtained m and angle phi. And now I can no plot, or I can obtain values of m and phi for the range of omega from 0 to infinity. Are you getting, guys? Yeah, any question here, Ben?
No, sir.
It's simple, right?
Yeah.
Okay, it should be at ease in beginning, so later no, you really don't find it difficult or no uh, difficulties in dealing with this. Yes, okay, good. Now we know this also mathematically. This I what I told you is from mathematics point of view. Once I know a transfer function, how should I proceed to find out its frequency response, right? The first step is replace no s with j omega. The new function will be called as a sinusoidal transfer function, and then you can quickly obtain the magnitude and phase angle, right? So now same thing. Okay, friends, that is about all about frequency response. No, and its no representation. Now we look into something called as correlation between time response and frequency response. So here we mathematically obtain a correlation, right? Because when we say correlation, we should have some mathematics, right, governing the correlation between them. Now we will see that this correlation between the two responses is possible for first and second order system only. This correlation between what? The time response and the frequency response is possible between first and second order systems. Moreover, in second order systems, you will see the correlation is there for no some limit on damping zeta. Under some limit on damping zeta for second order system, the correlation is valid. We will see that how to arrive at it. But this is what normally no you should be aware of, right? Between time response and frequency response. In time response, what we have, friends? Yes, in time response, normally what we talk about, we have two quantities, right? One is damping ratio zeta, another is what? Either omega n or omega d, natural frequency or damped frequency, right? So there will be some kind of no relation between this quantity and that what we see in frequency response. Frequency response, what are the quantities? Magnitude and phase angle phi, right? So we will develop some relation between this quantity and zeta and omega n, and that relation will be valid. We will see for some no limit condition on zeta, right? Let us see what it is. So let us begin with by taking a second order system here. Now we know in general a second order system is given here as it is, which we are aware of in its no standard form. The two characteristic parameters, undamped natural frequency omega n and the damping ratio zeta, right? Now, as we have seen in frequency response, we first have to obtain the sinusoidal transfer function. For that, I replace s here with j omega. So I get a sinusoidal transfer function. And when I do this substitution, this is what I end up with, right? In this expression. Now, what I do, I take out what here omega n common, right? And I substitute ratio omega by omega n equal to u, right, friends? So I will get something like this here. So if we have time, let us quickly see how we arrive this at this final answer. So I have got this as omega n square divided by j omega n square is minus omega n square plus j 2 zeta omega into omega n, right? J2 zeta omega into omega n plus omega n square. So if I take omega n square common, what I will be left with 1 divided by uh, yes, something is wrong here. Yeah. Here it should be what? Yes, Ben, what is wrong here? This should not be omega n. You are replacing s with what? J omega, right? So it should be only j omega square, right? Could you identify?
Yes.
It should not be suffix n here. It should be only j omega whole square. So it should be only minus omega square, right? When you are putting s equal to j omega, then it is minus omega square plus this, right? Now if I take omega n square common, then what I am left with? I am left with 1 divided by, it will be omega by omega n whole square, that I am calling as u. I am calling omega by omega n as what? U. So it will be minus u square plus 2 zeta. When I take omega n square common, 1 omega n in denominator gets cancelled here. So omega by omega n remains. That is called as u plus 1, right? And that is what we get, nothing but equal to 1 divided by 1 minus u square, that is the real part in denominator, and imaginary part will be j 2 zeta u, right? J will be as it is. So that is what we got it here, right, friends? So our sinusoidal transfer function I have replaced now in terms of a normalized no frequency u, that is given by omega divided by omega n. What is omega here? Ben, what is omega? Omega is the frequency of the input signal. What is omega? The input frequency. And what is omega n? Is omega n dependent on input?
No, so that's natural frequency.
That is the system parameter, right? Omega and zeta are what? Characteristics of the system, right? Once I have a
Yes.
system in my hand, I model it in terms of the values omega n and zeta, right? So omega n is its own parameter. So I am obtaining a normalized frequency u from no omega divided by omega n. So my sinusoidal transfer function has become now something like this here, right? T of j omega. So now I can very easily find out m and angle phi. What will be m here? M will be 1 by under root of a square. A is what here? 1 minus u square, its whole square, plus b square. B is what? 2 zeta u, its whole square, right? So this will be completely under root. So this will be magnitude m. And what will be angle phi? Angle phi will be minus tan inverse of what? 2 zeta u by what? Real term, that is 1 minus u square. So I have established m and phi both in terms of u, and now I am free to know obtain the values of these two quantities. Just one more minute I will take. Now when I put u equal to 0, what will be m here? When u is 0, m is equal to what from this equation? Let us say this is equation
One,
1,
sir.
1, and this is what? Equation 2, giving phase angle. So 1 tells us m is 1. And what is phase angle phi? When u is 0, it is tan inverse of 0. So tan inverse of 0 is theta is 0. When u is infinity, what is m from equation 1? When u is infinity, what it will be? It will be infinity in denominator, right? Anything in infinity will remain infinity. And 1 by infinity will be what? 0. And what will be angle phi? Angle phi will be what? Yes. When u is infinity, what it will be? Yes. It will be 1 by infinity. Yes or no? And what will be angle phi? Yes. My angle phi should be coming out to be what? In any answer here? Ben, quickly.
Zero, I think. So tan inverse of zero.
No, that will not be the case. I want here it to be what? I have done anything wrong mistake here. 2 zeta u. So it is 1 minus EU square, right? So my phi from here comes out to be what? Tan inverse of this is infinity, in anything in infinity is infinity, by what? 1 minus infinity square, right? So that has to be, why is that? Yeah, yeah, there is something to be explained. Let us hold on with this, right? How I am getting here, I am stating that if